Continuing with 1.3, more on functions and their graphs. We're being asked to evaluate h of -5 if the original h of x function, this is a piecewise function, so we refer to this as to the type of function it is. We'll soon see when graphed out what that looks like on a calculator. They always look kind of goofy, and these can look a little intimidating, but we'll take this one step at a time. So we're being asked to evaluate this x term when it's -5. We see two functions, x plus 4 if x is greater than or equal to -4. So this is one type of case we might fall into evaluating. We also have this second term or second piece of the function, negative parentheses x plus 4 if x is less than -4. So we have two cases that we might have to evaluate. So the question we have to ask is which case is going to make the most sense? Well, we know that we're evaluating where h -5 is using x to be -5. And so it's up to us to try and figure out which case this is going to fall into because we don't have a graph to evaluate yet. So we're really just basing this off of logic. So the question to ask is which one is this going to work in? So is -5 greater than or equal to -4? Or is -5 less than -4? I'll give you a moment to think that out. So you should be saying that if x is -5, we're going to have this second case work for us because if we evaluate this logically, -5 is definitely less than -4. If you're not convinced, check a number line. We have -1, -2, -3, -4, -5. -5 is definitely farther down on the number line, so this second case is what we're going to run with because this case works the best. So if we evaluate where x is -5, rewriting, we have to evaluate the opposite of the sum between -5 and 4. -5 plus 4 is going to get us -1. Keeping in mind that we're still subtracting that. So if we're subtracting a negative number, this should become the positive version or the opposite, which in this case would be +1. And this will be our final answer. So when h is evaluating -5, the outcome is definitely +1. For the visual on this, if we decided that we wanted to graph this out, and I'll make sure that you have the YouTube link on hand if you decide you want to see what this looks like when graphed. It's a little complex, but we see that we're evaluating the first function, x plus 4, if x is greater than or equal to -4, and that second function as well. When we see this graphed out, it looks as if it's an absolute value function, which is cool. Coming back again with algebra. If we hit second and then graph, evaluating -5, although the first line claims it's an error because we weren't working with that domain, we see that for the outcome on the second term, our outcome is definitely +1. So this is a logical answer based off of the graph, also based off of the table, and even just evaluating if we were plugging in. So this is good for us. With the second problem that we'll look at in this portion, we're being asked to determine if this function is even, odd, or neither. From the textbook, they are asking you to see pretty much which case it's going to fall into. It could be an even function, odd function, or neither. A little different than how you might recall knowing even, odd previously as far as types of numbers. So if the function is even, this is saying that if we were to plug in -x, we would still have that same outcome or the same original function getting us f of x. And a lot of this is going to come down to the exponent here. If we continue, we might see the odd setup, f of negative x, if that gives us the absolutely reverse or opposite type of function, that's considered to be odd. And the neither is just pretty much neither of these two options, where it's not equal to f of x, the original function, and it's not equal to negative f of x. And again, a lot of this is going to come down to the function. So if we get right to it, first evaluating f of negative x, the problem would look something like this. So just rewriting those x terms. We know that we have an exponent of 3 and an exponent of 7. These happen to be odd functions, or odd numbers rather. So even if we were to evaluate this as negative x times negative x times negative x, and then subtracting 7 versions of that same idea, we should hopefully see that negative x times negative x is positive x squared. But then multiplying with another negative x would change up everything, because negative x multiplying with x squared means that this would be a negative x cubed. And 3 would be multiplying with that. So that would change the first term to negative 3x cubed. If we follow through with the same idea on the right-hand side, we might even be able to jump the gun and say, well, 7's an odd number. Believe it or not, it's not divisible by 2, so we're going to have a leftover x squared term. So when we evaluate x squared times x squared times x squared, that would be subtracting 5 versions of positive x to the 6. But there's still that negative x term, which would switch up everything. So if we evaluate this, it's as if we're subtracting 5 versions of negative x to the 7th power. Negative times a negative would be positive. And we soon see that the coefficients for the x cubed term and the x to the 7th term are opposites now. Originally, they were positive for set 3. Now it's negative for 3. It was originally a negative 5 term for x to the 7th, and now we see it's a positive 5. So I'll give you a moment to think, which of these terms is it going to work with? Well, we know that we don't have the original f of x term. We can assume that it's going to be negative f of x. So if we evaluated f of negative x, this is equal to the opposite of the original f of x term. So we can conclude that this is an odd function. It's as if we took the original function, f of x, switched around all the terms and got here. So we can conclude that this is odd. Sometimes we'll see one term that's off or a few terms that are off. It really comes down to going bit by bit and checking if each term is going to be the opposite or the same. That's really crucial. Going more visual here, nice way to round out this section. Working and finding if there's a relative maxima, similar to a maximum point on this graph, or a relative minima. Minimum point, smallest point. We see with this function seen here, this is continuing way to the left and way to the right, so it's always going up or going down depending on how we look at it. We can assume that this continues in this fashion as it moves to the right, so it continues to just keep going up. Whereas if we go to the left, this continues to keep going down. So it's not as if there's one small point where it's just the smallest point or the lowest point. This is always improving, but we don't necessarily know where the maximum point is or where the smallest point is, because this continues in that fashion. So unfortunately for this one, there are going to be no maximas. And unfortunately, no minima points. This might not always be this type of situation. We might see some equations that dip down and then dip back up like this, in which case this could be considered a minima. We might see some equations that will move up and then kind of coast out a certain way, in which case this would be considered a maxima because it's the highest point nearby. Think of it as if you're at the top of the hill, but everything else is kind of below you. That's one way to think of this.